let's go ahead and get this session started. This is, uh, I believe, the fundamentals, foundation, and verification of machine learning systems. Our first talk will be by Jacob Laurel about a interesting approach for dealing with functions which aren't really differentiable everywhere. So go ahead.
Can everyone hear me? All right. All right. Hey, everyone. I'm Jacob. I'm a fifth-year PhD student at the University of Illinois, and this is joint work done with Rim Yang, Gaghandeep Singh, and my advisor, Sasha Misailovich. So, as we all probably know by now, we're in the midst of a machine learning revolution where AI is impacting almost all aspects of our lives. But we didn't really come here for a machine learning talk. As programming languages researchers, we care a lot about verifying things like safety properties. And this is something that's desperately needed in the machine learning world. And more specifically, for gradients. I mean, despite the fact that these are the backbone of most of modern machine learning, there is no general static analysis for verifying safety properties over these gradients. For things like Lipschitz robustness, where you want to certify a small Lipschitz constant, for things like analyzing an optimization landscape, where you want to certify the absence of a local minima or local maxima, and even things like certifying fairness or privacy of a classifier or sensitivity analysis, all fall under this umbrella of computing a bound on a gradient. So we're going to look more specifically at this Lipschitz robustness task. So imagine we have this neural network that controls this driverless car. And it sees some perturbed images of a stop sign. So imagine if this driverless car incorrectly decides to keep going. This would be quite a problem. And sadly, it's actually been shown to happen before from prior works. And this really stems from the fact that there's this highly complex decision boundary that governs this classifier's decision. And so we'll see how this actually corresponds to gradient information. So to zoom in a little bit more closely, imagine we have that image of the stop sign. And when it's not rotated, it corresponds to that red X along the classification surface. Now, rotating this image to the left by 10 degrees can change where along the decision boundary this network classifies that image. Likewise, rotating it to the right by 10 degrees can change where along the decision boundary this network classifies this image. So what we really would want to be able to do is actually bound the maximum amount of change in the classification output, which you can think of as this is a derivative. It's an amount of change. And we want this bound to hold for this entire local region of any angle between -10 and 10 degrees. So this bound actually has a special name. This bound for this gradient is actually the Lipschitz constant. And we will see more precisely what this is. So to kind of state this problem more formally, given a neural network F, a perturbation function P, in that case rotation, a parameter space that governs that perturbation's set of parameters, like the angles of the rotation, and we fixed an image, we want to find the smallest k, the smallest Lipschitz constant, that bounds the change in output, in the classification output of this network as a function of the perturbation amount. And so what we're really doing is we're actually bounding a gradient by a constant, and that's what this Lipschitz constant is. And we want something that supports arbitrary activation functions. We don't want to just be restricted to things like ReLU or tanh. We want something more general. And we want something that supports arbitrary arithmetic primitives, because this allows us to encode more complicated perturbations, things like rotations or applying contrast effects to an image. And furthermore, this parameter space can have multiple dimensions, especially when we have multiple perturbations acting on the image simultaneously. And lastly, and this is kind of a key motivation for our work, is that the composition of this perturbation with this neural network can have several points of non-differentiability. For instance, if the perturbation has the min or the max function, or the network has a ReLU activation function, you can have points of non-differentiability mixed in with something that is differentiable, like a tanh activation. And so how do we resolve this? So how can we actually get an analysis that is fully general and arbitrary perturbations, arbitrary activations, and even goes beyond this Lipschitz robustness task, where it's not just an analysis for this Lipschitz task, but can go to those other gradient tasks that I mentioned. How can we get something that's compositional so that we don't have to hard code things or just fix it for a specific type of analysis? And how can we get something that's efficient? Because at the end of the day, we're going to have to actually apply this to a real-world machine learning system. And as we've seen, these are actually quite large. So we're actually able to get all of these things with DeepJ. And this is this differentiable programming framework that we propose. And it leverages a custom forward mode analysis that's built atop an abstract domain for dual numbers. And we'll see how taking this differentiable programming viewpoint gives us all of these things simultaneously. And this is really an example of where the programming languages mindset gives us so much more than what machine learning people are used to. So just the language is given as follows, where it's pretty much a standard differentiable programming language, but we have this branching primitive. Now this is tricky because you can now start to encode things like the ReLU function, which has this point of non-differentiability at 0. And so its classical Jacobian is not defined there. So we need to go beyond the classical Jacobian if we want to reason about this in a formal, principled, mathematically sound way. And we do this by defining our semantics over the Clark generalized Jacobian. And the benefit of this type of Jacobian is that it actually can handle differentiable and non-differentiable, though still Lipschitz continuous functions. Furthermore, the benefit of the Clark generalized Jacobian, as opposed to some other types of generalized Jacobians that have been proposed in the literature, is that the Clark Jacobian still retains a lot of useful properties and allows us to obtain useful information like Lipschitz constants. So just a reminder from our calculus class, this is the standard Jacobian, which is this matrix of all first-order partial derivatives. And the Clark generalized Jacobian goes a step beyond this, whereby if we have a point for which the classical Jacobian is undefined, what we can actually do is take a sequence of points that converges to that point, such that for every point in that sequence, the classical Jacobian is still defined, and then take what that sequence of Jacobians converges to. And we can take the convex hull over all such limiting sequences of Jacobians. Now this may seem like a lot and quite a complex definition, but it actually agrees with our intuition. So if we take this line, this simple line 2x, slope 2, this does have a well-defined classical derivative at 0. And so the Clark generalized Jacobian coincides exactly with the classical derivative when the function does have a classical derivative at a point. But if you have this ReLU function, which does not have a well-defined classical derivative at the point x equals 0, the Clark generalized Jacobian is still able to define a generalization of the derivative at that point. In this case, it's the interval 0 to 1. So the exact Clark Jacobian, though, is not actually computable. So what we have to do is compute a sound over-approximation of it via abstract interpretation. And we do this with a forward mode analysis. It's sort of an abstraction of forward mode auto-differentiation. And this is ideal for low input dimension, and it will leverage an abstract domain built atop dual numbers. So just a little bit of what is a dual number? Well, these look kind of similar to complex numbers, and they sort of are, except with complex numbers, the imaginary unit squared equals -1, whereas with dual numbers, this epsilon unit squared is 0. And we'll see actually why this makes sense. So recall a first-order Taylor series from our freshman calculus class again. So if I'm to Taylor expand this function about this point a plus b epsilon, where here epsilon intuitively represents some infinitesimal perturbation, and that's also why you can think of some infinitesimal quantity squared as even smaller, so you can think of it as being 0. So if I expand it as follows, but I also know that epsilon squared is 0, then I can get rid of all of those higher order terms. So ultimately, what I'm left with is this. So to evaluate a function over a plus b epsilon, I can evaluate that function over a, and then evaluate that function's derivative over a, and then multiply by b, which will also intuitively correspond to the chain rule. So what I'm really doing here is I'm propagating a first-order Taylor polynomial through the function, where I have both the function's value and the function's derivative value, that tuple as a first-order Taylor polynomial that gets propagated through the function. So what we do is actually we lift this to the interval domain in the form of dual intervals. So just as one has arithmetic rules for dual numbers, we can lift all of those standard arithmetic operations to the interval domain. So we can have dual interval addition. And the other arithmetic primitives follow analogously. So this intuition of this first-order Taylor series interpretation still holds for intervals. And we'll see why this is quite powerful. So more precisely, we have our custom abstract domain where we associate to each variable a dual interval. And we define abstract transformers for all of the primitive arithmetic and functions. And one caveat about our analysis is that because we have this branching primitive in our language, we have to define a join that will soundly over-approximate the true Clark Jacobian. And we'll see why our join is actually quite natural for this problem. So here is the signature of the abstract interpreter. And this is the function, this first argument is the function that we want to abstractly differentiate. And this function need not be differentiable in the classical sense. For instance, it could actually be a ReLU and have points of non-differentiability. This second argument is the input dual interval, which is m-dimensional. And you can intuitively sort of think of this as the state. And this final return value is the output dual interval. So to kind of go through the rules briefly, these are the base cases of our abstract evaluation. And the base case, first base case is just primitive variables. So the ith variable is just the ith component of this multi-dimensional dual input interval. The abstract evaluation of a constant is we just lift that constant to its respective dual interval. The abstract evaluation of a primitive C1 function, well, a C1 function is a function that is continuous and has a continuous first derivative. So, and these are primitive functions in our language, so we'll know their analytical form. They could be things like sine or exponential, those type of primitives. So because of that, we know both its analytical form as well as the analytical form of the derivative. And so we can evaluate both of those over the interval domain. And that taken together as that tuple is the dual interval abstraction of that primitive function. So knowing those base cases, we can actually build up more complicated functions. So we can take the Cartesian product of two functions by simply just abstractly evaluating each function separately and then taking the Cartesian product of those output dual intervals. We can do something similarly for the addition of two functions, multiplication of two functions, division with a function, and composition of a function. So this is where we get compositionality. So now I'm going to get into a big detail of our analysis, which is this branching and how we handle it abstractly. So as I mentioned, we have this join operator, and we join both the real and the dual parts. And by joining the dual parts, we're intuitively joining the derivatives and taking sort of the convex hull over derivatives. Because as I mentioned, this dual part you can think of as being the derivative component. And this is actually quite nice because it does coincide with that definition of the Clark generalized Jacobian that I gave, where we have to take the convex hull over all possible Jacobians that we could end up with. And so we can put that actually into the branching rule as follows, where we can now define the abstract semantics of a branch. And so to give a more detailed example of this, this is how we would encode the ReLU function in our abstract semantics and how we would encode the max function, both of which are non-differentiable at points. So to take this example a step further and to go beyond just individual functions and see how this thing actually works end-to-end, imagine we had this neural network. And we also apply this contrast variation perturbation to the image. So this is a different perturbation than rotation. Instead of rotating an image, what it does is it models contrast effects when you sharpen the contrast between pixels. And so instead of propagating the original pixel values, x1 and x2, through the network, we actually propagate their perturbed values, x1 prime and x2 prime, through this network. And because we want the Lipschitz constant to be with respect to the amount of perturbation we apply, which in this case is theta, we have to differentiate with respect to theta. Because we want the change in output as a function of the change in perturbation amount, theta, not the change in the pixels themselves. So the pixels themselves are constants, and that's why their dual part is just the degenerate interval 0, 0, whereas because we differentiate with respect to theta, its dual part is the interval 1, 1. So the first step is we abstractly propagate these inputs through this perturbation function. this gives us an abstraction of the perturbed inputs. And now with these perturbed inputs abstracted, we can propagate those through the network. We propagate those through the first layer of the network, and then through these activation functions, and then through the next layer of the network, and through the last activation functions. So what we'll do then is we will take the respective dual components of these outputs, and taken together, that forms the interval over approximation of the Clark generalized Jacobian. Now from this, we can recover a Lipschitz constant, which bounds the amount of change in the output as a function of the amount of contrast variation that we apply. And we also note that this bound holds for any amount of contrast variation in that interval 0 to 0.1, so it holds over this entire range. So just to kind of briefly mention the theoretical results of this analysis. So in the paper, we do in fact prove that this interval over approximation does indeed over approximate the true Clark Jacobian. And as I mentioned, we took a forward mode analysis, which is sort of an abstraction of forward mode autodiff, and as opposed to taking a reverse mode analysis. And so we do prove the correctness of this forward mode analysis, and that's also in the paper. And one thing that I want to highlight is that because we're working with intervals, what we can actually do is kind of a standard trick where we actually partition that input interval into disjoint partitions, and then apply the analysis on each of those partitions separately. And then we can take the union of all those results at the end. And this actually can allow us to get a little bit more precision, because interval arithmetic can become more over approximate. So when you shrink the intervals, the analysis can stay more tractable. So this actually allows our analysis to improve the precision. So just some applications of our analysis. So beyond this local Lipschitz robustness with respect to a parameter of a non-differentiable function that I've described, we can also analyze things like optimization landscapes, which we did in the paper, where you can certify the absence of a local extrema in some optimization landscape. And really, it's quite general, actually. You can use this for any task where you have to reason about the range of derivatives, but when you can have these kind of pathological points of non-differentiability, like in a ReLU, or like the absolute value function or the max function. So it's actually quite a general framework. So just to briefly describe the experiments, we evaluated our approach on multiple different architectures, both convolutional and fully connected. And the largest contains about 62,000 neurons and about 2.5 million edge parameters. And we evaluated on both the CFAR and IMNIS data sets. And as a baseline, well, because no other work can compute what we compute, it wasn't immediately clear what a baseline would even be. So what we did is we compute the local Lipschitz constant of the perturbation function, and then we multiply this by the global Lipschitz constant of the neural network, because that's what most standard Lipschitz robustness literature does, is computes these global Lipschitz constants. And so additionally, we analyzed three different types of perturbations: haze, contrast, and image rotation. And I'll get into each of those. So haze additively applies some amount of perturbation to each pixel. Now, the contrast perturbation is a little trickier in that it does not apply the same amount of perturbation to each pixel. So the first thing that we want to notice is that this is a function that has points of non-differentiability because of this max and this min. And then the second thing to notice here is that some pixels stay exactly the same after applying the perturbation. Like these white pixels in the background stay exactly the same. But some pixels, like the ones on the horse's body, can become much different in that pixels that were maybe a medium red or a medium brown can become dark red or dark black even. So because we've changed pixels non-uniformly, this adds a different, an extra level of complexity to the problem. And we want to note that prior to our work, no other work could work under this assumption. All prior Lipschitz robustness work prior to ours was restricted to cases where you perturb each pixel by the same amount uniformly. So no prior work can handle this non-uniform setting that we're interested in. And then this property also holds for the rotation perturbation. As we can see, many of the pixels stay exactly the same, yet other pixels change drastically. So it's a very non-uniform perturbation on the pixels. And one thing that I'd like to note here is that this interpolation function is non-differentiable. It contains the max function, so it definitely also has these kind of pathological points of non-differentiability. So just to briefly go over the experimental results, x-axis represents the interval width of the perturbation range that we wanted to certify. The y-axis represents the Lipschitz constant, where smaller is better. And then this brown line at the top represents the baseline. And as I mentioned, we can optimize our analysis by applying more splits. So these colored curves represent Deep-J, but with different numbers of splits. And as we can see, more splits leads to lower Lipschitz constant, hence more precision. So so this trend holds over all benchmarks and all baselines that we analyzed. So for any of the networks, any of the data sets, we can see that Deep-J is still significantly more precise. And even when we analyze the composition of results, the composition of multiple perturbations, this result still holds. And here we can see that with two perturbations that we've applied compositionally instead of just one at a time, we've composed two together. We can see that for all benchmarks, all networks, all perturbation combinations, Deep-J is still significantly more precise than the baseline. And it's still quite fast, taking for an individual perturbation just a few seconds. And even for a composition of a couple perturbations, it's still not prohibitively large. And then just to kind of explain what else is in the paper that I couldn't get to is that we have full proofs of soundness of all the transformers, as well as a little bit of complexity analysis. And we also analyzed another task that goes beyond Lipschitz constants. We analyzed local optimization landscapes to certify the absence of local extrema. So just to summarize, Deep-J provides the first abstract interpretation of Clark generalized Jacobians. And this gives us a lot of generality and a lot of compositionality. And this forward mode that we use is highly efficient. For a large amount of neurons, it's still quite fast. So because we're forward mode, we're fast. We fast forward the computation of Clark Jacobians with dual intervals. So with that being said, thank you.
Thanks so much. Great talk.
Thank you.
Do we have any questions? Okay, 1 second. I'll get right out there.
Thank you for the excellent talk.
Oh, thank you.
I see that you use the interval domain, which works reasonably well, but is also known to be not super precise.
Yes.
Can this approach be generalized to more precise abstract domains, such as?
Oh, like polyhedra or zonotopes?
Exactly.
Yeah, so that's actually a great question and something that we're currently trying to investigate. And so what I would mention there is that because in that definition of the Clark generalized Jacobian, you have that convex hull, you would need to make sure that whatever abstract domain you have can soundly over-approximate that convex hull when you have to take the join of the derivatives of both the true and the false branches. So making sure that you can soundly over-approximate that convex hull would be the key factor that you'd have to make sure that abstract domain can over-approximate. So I guess this may be a little trickier with things like with polyhedra, but it may not be. But that is definitely the key concern that you have to worry about with working with this generalized Jacobian as opposed to just the standard Jacobian. But yeah, that's a great question.
It was a very interesting talk.
Thank you.
So it seems to me that what you'd be worried about if you're using the analytical form of the functions is not discontinuities, but wild jumps of the derivative itself, huge up spikes kind of shapes. And which means if your functions look kind of roughly, if the sphere ball is bounded, that'd be good behavior. So are you counting on that? And if you are not counting on that, why wouldn't something like sampling also work for computing the Lipschitz constant?
Mm-hmm. So that's a good question. So pretty much all of the models that people in machine learning care about are Lipschitz continuous, or at least locally Lipschitz continuous. So you don't typically have to worry about like jumps of actual discontinuities. But you had mentioned that you can have these steep jumps in the gradient or in the function, and therefore a large gradient, which means a large Lipschitz constant. So that is sort of unavoidable, especially when you have more layers in your neural network. You can express things that have much larger Lipschitz constants, and very often a lot of these networks do exactly that. So that is unavoidable, that you're going to have large Lipschitz constants. As to your question about why not sampling, So there are some works that for not our task, but for simpler tasks do sampling. But what they found was that for those works, they significantly underestimated what the true Lipschitz constant was, because it's unsound to do that, and so you run the risk of under-approximating what you're really after. But no, that is definitely an interesting line of work. Yes.
So we have two quick questions online.
Sure.
Then, sorry, we're going to have to keep moving. The first one's from Neil
Okay.
Krishnaswamy. Hopefully, yeah. Sorry, it grays out the text on this. The question is, well, first he said nice talk, and asked if mentioning that Clark derivatives were developed for convex optimization, and neural networks are not necessarily computing convex functions. Can you give an intuitive reason why Clark derivatives still work here?
So that is a great question. And the Clark derivatives were in fact developed in about the 70s, I believe, for non-smooth optimization. Now, the reason why they work so well here is that all you really need for the Clark derivative is this function to be locally Lipschitz continuous in the region that you're interested in computing the Clark derivative for. And for all of the perturbations that we analyze, like this rotation, which has a bilinear interpolation implemented with the max function, this contrast variation, all of these perturbations that we're interested in actually satisfy that. So that was actually quite an interesting insight. And then these networks also are pretty well behaved, especially ReLU networks, which are basically just piecewise linear functions. Hence, they also have well-defined Clark Jacobians. So it was just kind of a serendipity that we looked at these perturbations that people in the machine learning space had cared about, and found, hey, these satisfy all the properties of what you need a Clark derivative for a Clark derivative. So this actually represents a general way to address these. And then when you think about it very generally, you kind of get all of these